what we do is we will observe a special application of electromagnetic waves, that is nothing but fiber optics or optical fibers. These optical fibers are the medium which will be useful for transmission of a light wave. So they are not, it's not exactly the electromagnetic wave, it will not contain the electric field and magnetic field, but it will comes under our electromagnetic spectrum. So it comes under our light spectrum, visible light spectrum or ultraviolet light spectrum, like that. So what are different conditions which are to be satisfied to transmit a light ray from one location to another location, and what is the medium for that one, what are different types of medium and applications of this, we will discuss in this session. Now observe, what is an optical fiber? So an optical fiber is essentially a waveguide for light, that for the transmission of light signal it will be useful as a waveguide. Waveguide is nothing but a physical waveguide which will be useful for transmission of light ray from one location to another location. It consists of core and cladding. That later I will show you the complete construction of our optical fiber cable. That initially just you remember that it consists of a core and clad and a particular material like a plastic material which surrounds this core and clad for the protection purpose. And the total internal reflection, the index of refraction of the clad is less than that of the core. The index of refraction is nothing but the refractive index, the refractive index of the core and the refractive index of the clad. So these two are different, and later I will give you which one is more and which one is less. Here itself the point is given that the core refractive index is more than clad refractive index. And so with this one what we can get is the total internal reflection. So for that what we are doing is we are taking two different refractive indices for these two. And here what are different sources which emits light? The light emitting diode, that is, this is one of the source, and a laser diode, this is another source. These two will be useful for generation of our light in according with the electrical signal that what we have. Now what are a few applications of our optical fibers? The applications of our optical fibers are, it has greater bandwidth, that when compared with our waveguides which are useful at microwave frequencies, when compared with the transmission lines, the bandwidth of our optical fiber cable is very, very high. We can transmit thousands of signals through a single cable. And lower loss, the attenuation or the loss which is provided by the optical fiber is very, very less when compared with remaining all. And immunity to crosstalk. So whenever there are more signals are being transmitted in a particular line or a single line, we may observe some crosstalk. That such type of crosstalk is very, very less in our optical fibers. And no electrical hazard will be there. That clearly there will be no electrical signal, there will be no voltage and no current in this particular medium. So no electrical hazard will be there because of these mediums, or that is optical fibers. Now observe what is the basic structure of our optical fiber, how it will be made and what is the construction. Here if you observe, the optical fiber is constructed with a core. Core is nothing but a material which can be useful for transmission of the light ray through this one. So this is a core which is made up of either plastic or some glass type material. So in this particular core only the light ray will be completely transmitted through total internal reflection. Now if you observe, this is the front cross sectional view and this is the side cross sectional view. If you are observing the front cross sectional view, the centermost one is nothing but the core, and here this is the core. So within this core the light will take continuous reflections like this. As I am showing, a continuous reflections will be there within this particular core, and the signal will be transmitted from our source to the destination. And the next one is clad. This clad has a less refractive index when compared with the core. As this is less refractive index, obviously some refraction will be taking place at the boundary. What we do is we will ensure a few conditions in such a way that there will be no refraction at the clad and the completely reflection will be there within the core. So what we do is we will make this clad with some other material which has another refractive index than core. And the top one is, and that is this one. This is a material which is made up of some plastic which will be used as a jacket for this core and clad, which is used to protect our optical fiber cable. The optical fiber cable is very, very narrow in its dimensions, very, very thin its dimensions, and sometimes that may be of order micrometers, so that it will be very delicate. This jacket we will be used to provide protection to that particular structure. So this is our optical fiber cross sectional view. Now observe what is the basic block diagram of our optical fiber communication system. So this is the basic block diagram of our optical fiber communication system. Here a signal source will be there, same as our remaining communication systems. Here also we have a signal source. This signal source will generate the signal which is in the form of voltage and current. That is the basic system that what we have. That voltage and current system will be converted as an optical system or optical signal using this optical transmitter. It will takes the voltage current as the input and gives light as the output. That light will be fed to the optical fiber cable using some connectors. That in the optical fiber cable the light signal will be transmitted, and once again that will be received using our optical receiver. This optical receiver will convert the light signal which is received into the electrical signal, which is in the form of voltage and current. That voltage and current will be observed by the taken by our signal destination and will be demodulated or decoded, whatever it may be. So in this one completely, this optical fiber cable is very important. Without this optical fiber cable, this is not at all possible. It is not at all possible to transmit this signal in our optical communication system. Now what is an optical fiber? Already we discussed this. Optical fiber is nothing but a waveguide which will be useful for transmission of our light ray. Now how it is made, what are the characteristics? Observe. So optical fiber is made from thin strands of either glass or plastic. So glass or plastic strands will be taken. It is very thin. Sometimes, as I said, this will be in the order of micrometers, and it has a little mechanical strength. So it must be enclosed in a protective jacket. That what we observed in our diagram. Often 2 or more fibers are enclosed in the same cable for increasing the bandwidth and redundancy, as in case of the fiber breaks. That we can club many number of optical fibers, and that the more number of optical fibers can be kept in a single location. It is also easier to build a full duplex system using 2 fibers, one for transmission in each direction. So clearly we can establish a full duplex system also with this optical fiber system. Now observe what is the basic principle for transmission of signal in our optical fiber system. The basic principle is total internal reflection. Observe here. What is total internal reflection? If you observe this particular diagram, you can easily understand what is total internal reflection. Total internal reflection means reflecting the signal within the core itself. So prior to that, what happens? Let us imagine a signal is hitting the boundary of our 2 mediums. This particular one is one medium with refractive index N2, and this one is another medium with refractive index N1. Whenever the light hits the boundary of these 2 mediums, obviously because of the variation in the refractive index, it will take refraction in the second medium. It transmits to the second medium, but it refracts because of variation in the refractive index. Now let us take, this is the incident angle and this is the refraction angle. These two will be taken with the normal. So theta 1 is the incident angle, theta 2 is the refraction angle. Now what we are doing is just slightly we are varying the incident angle. What I am doing is just I am taking another incident angle that is more than the previous one, that I enhanced or I increased the incident angle. Whenever we are increasing the incident angle, this refraction angle will be increased. So if you are increasing theta 1, theta 2 also increases. At some angle, what you can observe is this refracted ray will coincide with the boundary of our 2 medium. So clearly at some incident angle, as you are increasing this one, at some incident angle, this refracted ray will incidence with the boundary. Now this particular angle is called as critical angle. That this angle is very important. Now up to this critical angle, it will take refraction to the clad. So from core, it always takes refraction to the clad. Whenever we are applying the signal with this critical angle, it is not taking reflection, it is not taking refraction, just it is coincides with the boundary. Right? Now what I do is just I will increase this particular angle further. So if you are increasing this particular angle beyond this critical angle, then this signal will be reflected within this particular core. So the signal what we are observing as a refracted signal earlier is now becomes reflected signal within the core. So always we are supposed to take the angle which is greater than critical angle for this total internal reflection. That the angle of incidence is greater than always critical angle theta c. That this theta 1 must be greater than theta c, then the signal will be completely reflected within the core itself, and once again it hits the boundary and reflected within the core itself. That's why the total internal reflection will be taking place and no signal will be lost as a form of refraction. So for that, the Snell's law will be useful for understanding this total internal reflection. So the angle of refraction, angle of reflection, and total two refractive indices will be related with this equation n1 sin theta 1 is equals to n2 sin theta 2. This is called as Snell's law. Using this Snell's law, we can observe the critical angle also. Now observe numerical aperture. What is numerical aperture? Numerical aperture is nothing but the angle, how much angle it is accepting, a particular optical fiber cable is accepting. This is called as numerical aperture. That beyond this angle, just you observe this figure. If you observe this figure, it is very easy. Just you if you are applying the signal with this angle, then only it accepts the signal. So beyond this angle, it will not accept the signal. So beyond this angle also, it will not accept the signal. So this angle is called as numerical aperture, that will be taken in degrees. That twice of the numerical aperture is called as the angle of acceptance. So this total angle is called as the angle of acceptance. The name itself indicating that it is accepting the signal for this particular angle only. It is given as under root of n1 square minus n2 square for our optical fiber cables, where n1 and n2 are the refractive indices of core and clad respectively. And what are different modes of operation for our optical fiber cables? So in the optical fiber cable, same as our waveguides which are observed in our microwave frequencies, here also different modes will be there. That only one signal will be transmitted through the optical fiber cable. This is called as single mode. So more than one signal will be transmitted. This is called as multi-mode. This is completely depend upon the structure of our optical fiber cable. If the optical fiber cable core is very narrow or very thin, then only one signal will be transmitted through that one. That the angle of incidence is very less, and the acceptance angle is also very less. So the signal which is entered with that particular angle will be taken into total internal reflection, and that will be transmitted through the optical fiber cable. So in very narrow or very thin optical fiber cables, a single ray will be transmitted. They are called as the single mode optical fiber cables. And multi-mode optical fiber cables, that little bit the core diameter is more when compared with our single mode. So since the core diameter is more, acceptance angle is more. As the acceptance angle is more, so more number of signals can be transmitted with different angles. So for different angles, more signals can be transmitted, that a multi-mode propagation will be taken place. So whenever we are considering a multi-mode propagation, sometimes the dispersion will occur. Dispersion is not appears in our single mode propagation. Now observe the types of fibers. So as we discussed, so these two, if you observe the figures, these two will comes under step index, and this will comes under graded index fibers. Just you remember these words. Step index means the variation of the refractive index for the core and clad is abrupt. We will take abrupt change. For the entire core, only one refractive index will be there. For entire clad, only one refractive index will be there, and the change is abrupt at the boundary. And this is a single mode fiber. It has a very narrow or very thin core, and this is a multi-mode fiber which has a little bit broader core. And here also it is a step index fiber, that only a single refractive index will be there for core, and a single refractive index will be there for clad. But for graded index fiber, the core refractive index will be gradually increases to the center and then decreases to the boundary. That this is the variation of our refractive index for the core. So if you are transmitting multi-mode signal, that is a number of signals in a graded index, then the dispersion will be little bit less when compared with the step index fiber. So what are different losses which are which can be observed in our optical fiber cables? The losses which can be observed in our optical fiber cables depend upon the structure of our optical fiber cable, the material what we are using for the manufacturing of optical fiber cable, and how much bending it is taking. This is also describes our losses. Let's imagine once again. So we have a critical angle. So beyond that critical angle only the signal will be accepted, right? So then only the total internal reflection will taking place. If we are changing the shape of our optical fiber abruptly, then this critical angle will varies. So if the angle falls below the critical angle, then that will goes to the clad, that is taking that's called as the refraction to the clad. Then this will be taken as simply loss. Like that, so if you are bending the optical fiber cable, a loss will occur, or because of the irregularities in the core, the losses will occur. Because of the irregularities in the clad, the losses will occur, or because of the manufacturing materials, the losses will be appeared. Now observe, the losses in optical fiber results from the attenuation in the material itself. that is the irregularity because of the material or the scattering of the wave at the clad walls or some other materials. And the bending of optical fiber is too sharply can also cause the losses. This is the point that what we discussed. And losses very greatly depend upon the type of fiber. For a plastic fiber, the losses are 100 dB per kilometer, and for graded index multimode glass fiber, the losses are about 2 to 4 dB per kilometer, or for a single mode fiber, the losses are very less because there are no adjacent waves to disturb and disperse. That's why the dispersion is very less, the losses are also very less. That's a 0.4 dB per kilometer or less than that one. This figure describes the type of losses when it is abruptly bent. So whenever the wave is traveling with total internal reflection, if the bending is taking place, the critical angle is varied. Since the critical angle is varied or the angle of incident is varied, it's obviously that it takes some refraction. So this is due to the bending. Now this gives the losses appears at different wavelengths. So here there are two windows, that is 1320 and 1550 nanometers. The wavelength is taken in nanometers. At 1310, it's a 1310 nanometer and 1550 nanometer, the losses are very less. So in most of the practical cases, what they do is they'll use these two windows, 1310 nanometer and 1550 nanometer for practical applications. And we are discussing about different optical sources. So what are different optical sources? Optical source is nothing but a source which can be useful for generation of the light, nothing more than that. So what we have to do is just we have to search for different optical sources which can be useful for our optical communication. There are two major optical sources. They are LEDs, light emitting diodes, and laser diodes. And so in these two, what happens? So based on the input what we are applying, that is some voltage and current we are applying, it generates the light. Right? So depend upon the signal what we are applying, that's a bit depend upon the signal which is coming from the electrical circuitry, they will generate a corresponding light source. So what we do is just we will discuss about those two. Light emitting diodes. So what is light emitting diode? In a normal PN junction diode, so whenever we are varying or whenever we are increasing the potential, you can observe some heat, that the heat will be generated from the diode. After that one that may burn, right? So but here in LED what happens is instead of generating heat, it will generate photons. Photons are nothing but the light particles. So in a forward bias operation, that a light LED operates in forward bias. In a forward bias operation, instead of generating the heat, it will generate light. So this is the simple structure of our LED. This LED will contains an N type of aluminum GaAs, gallium arsenide, and P type GaAs, and some insulating materials will be there. So whenever it is connected in a forward bias, at the junction a light will be generated. Now another source is laser diode. So laser diode is also useful for generation of light, but here the laser diode light is very sharper than our LED. It's a very narrower than our LED. So here this laser diode generates a coherent intense light of a very narrow bandwidth, and a laser diode has an emission line width of about 2 nanometer. It's compared to 50 nanometer of our common LED, and laser diodes are constructed with same materials, same as our LEDs, but operate at high current levels. Just you observe the construction of our laser diode. This is the laser diode construction, and they are also using aluminum gallium arsenide, N type material, P type material, but they will use very high currents, and by applying the very high currents, a narrow output, light output will be generated here, and this is very much sharper than and intensity than our LEDs. Now whenever the signal is transmitted using in our optical communication, we are using LEDs or lasers as the sources, and what are different detectors which can be useful for our optical detection. Here we have, just observe this slide, here we have PIN diode. PIN diode is nothing but the P type material, intrinsic material, N type material. This is a special type of diode which will be useful for photo detection. Photo detection is nothing but converting our photo signal, that's something but the light signal, into electrical signal. Depend upon the intensity which is placed on this diode, it will generate the electrical signal. So if more light intensity is there, it will generate the corresponding voltage and current, and like that, depend upon the light intensity which is fallen on this one, the voltage and current will be generated, that will be applied to the circuitry. So this is a simple optical detector that what we use. Basic concepts in optical fibers, we will try to answer a few multiple choice questions. Observe these questions and try to answer them. The visible light's wavelength ranges from, so this is directly taken from the frequency range. that the visible light frequency wavelength ranges from, always remember this formula or remember this value, 0.39 to 0.77 micrometer. So 0.39 to 0.77 micrometer is the answer. Next question. Sum of these is unity. Option A, reflectivity. Option B, reflectivity plus refractivity. Option C, reflectivity plus refractivity plus transmittivity. Option D, any. Before going to this, just before answering this, just you observe what are the parameters given to us. Whenever the light is transmitting in our optical fiber, it may take refraction if the angle is not suitable. It may take reflection within the core itself, and it will take transmission to the clad also. So here the incident light ray is 1 and it will be divided as a refracted ray, transmitted ray and or reflected ray. So input is equals to sum of these three, right? So what you can say is, as per our probability, if you are adding these three, you may get 1. So sum of these three is unity, that is the reflectivity, refractivity and transmittivity also. That option C is correct answer for this particular question. Now observe the next one. Snell's law relates light reflection, option B light refraction, option C light transmission and option D light absorption. What is Snell's law? Snell's law always relates the refractive indices of our materials with the angle of incidence and angle of refraction, right? So whenever there is a refraction in another medium, the refraction angle we are considering, the incident angle we are considering, n1 sin theta 1 is equals to n2 sin theta 2. This is simply Snell's law. So here the Snell's law always useful for observation of or based on or refraction. So here light refraction is the correct answer, that is option B is correct. Now comes to the next question. Optical fiber operates on the principle of A, total internal reflection, B, Tyndall effect, C, photoelectric effect and D, laser technology. So among these four, directly we can say that the optical fiber communication system always depends upon total internal reflection. So option A is correct answer for this particular bit. Now observe another question. Light from free space is incident at an angle to the normal of the facet of a step index large core optical fiber. The core and cladding refractive indices are n1 is equals to 1.5 and n2 is equals to 1.4 respectively. That the figure is shown here. The maximum value of theta I, that is nothing but this angle. This is not incident angle. Don't take this one as incident angle. This is theta I. This is nothing but the acceptance angle, half of the acceptance angle. The maximum value of theta I for which the incident light will be guided in the core of the fiber is option A 16.51, option B 32.58, option C 64.28 and option D none of the above. Here clearly observe what's the data given to us. N1 is given to us, the refractive index of core, N2 refractive index of clad. So directly you are supposed to calculate the acceptance angle. So what is the formula for acceptance angle? Directly we have sin theta I is equals to sin inverse of n1 square minus n2 square. This is the formula for acceptance angle that what we have. Now by substituting n1 and n2, we will get theta I is equals to 32.58 degrees. So for this particular problem, option B 32.58 degrees is the correct answer. So these are few multiple choice questions we can answer from our optical fiber communication systems.